Recently, I've been messing about with PyMunk, which is a physics library for Python. For my first PyMunk project, I chose to make a pool game, and that's what I'm going to cover in this tutorial. This isn't a pool game in the traditional sense. It's a single player game, and the aim is to pot all of the balls, including the black ball, in any order. The catch is that you have 3 lives, and every time you pot the white, you lose a life. If you enjoy these tutorials, then remember to hit the like button and subscribe to the channel. If you haven't heard of PyMunk before, here are a few demos taken from the PyMunk website that show what it can do. In this one, you control a little green tank with your mouse. As you move around, it collides with various objects and pushes them out of the way. The collision works at different orientations and angles and with a few objects at the same time. In this one, you can left click to create circles which automatically fall due to gravity. You can then draw lines with the right mouse button to create obstacles. PyMunk then takes care of all the physics and collisions in the background. The next one is really cool and probably my favorite demo. You start off with a bunch of circles inside this pink space. You can then draw to extend the space. The boundaries of it are automatically updated and the circles then react to the new boundaries. You can add more circles and you can create various extensions to the boundaries. I think this is a really clever demo and it shows how PyMunk can respond to dynamic changes in the environment. Before we start, you need to make sure that you have Pygame and PyMunk installed. You can do this easily using the pip command within the command prompt. Next, we need to set up the folder structure correctly. I have my root folder called pool tutorial. Within here, I've got my main.py file where I'll be typing all of my code. And next to it, I have an assets folder. Inside that is the images folder. And inside that are all the images that we're going to use for this game. You can download all of the assets from the video description, but you need to make sure that they're organized in the same way to avoid any errors. Before I get into PyMunk, I'm going to set up my Pygame window so we've got a way of visualizing the PyMunk objects. We begin first by importing Pygame, and then initializing Pygame by running pygame.init. Next, we need to define a couple of variables for the game window. So these are screen width and screen height, which I will set to 1200 and 678 pixels. Next, I'll add a comment here to say my game window, and I will create that by assigning it to a variable called screen and calling the function pygame.display.set_mode, where I can pass my screen width and screen height. The next thing I want to do is add in a little caption at the top. So that's going to be the text that's up here. And I do that by saying pygame.display.set_caption. And the title I'm going to give this is just going to be pool. Now, if I run this code, you see a game window pops up for a second and then closes back down again. The reason for that is the Python is running through this code line by line and gets to the end and that's the code finished. What I need to add is a game loop. And this loop is going to continue running and it'll mean that the game window stays on the screen. So I'll add a little comment to say game loop, and within here I'll define a starting variable condition. This variable is going to be called run and I will set it to true. I can then create my loop, which will be a while loop set to the condition of run. As long as the run variable is set to true, or it's equal to true, this while loop is going to continue running. That will mean that the game window will stay on the screen and it will stay active, but I also need a way of exiting the game. And I'm going to do that by adding in a condition for clicking the X in the top right corner. Now for that, I need to add in an event handler. I'll add a comment to say event handler, and I will iterate through each of the events. We'll say for event in pygame.event.get, and then we can look for a specific event type. I'll say if event.type is equal to pygame.quit, which is the event of clicking on the X in the top right corner, then I just need to set that run variable to false. At this point, the while loop is no longer going to meet the conditions and it's going to exit. So the last thing to do is to add pygame.quit right at the end and not indented. If I run this code again, I get my game window up, I get this little caption at the top that says pool, and if I click the red X, it closes the game down. Before we can run any simulations, we need to create a PyMunk space. We can then define various parameters for the space, which will control how the objects behave. For example, we can define the gravity, and PyMunk will automatically apply that gravity to the objects that we create. once the space is set up, we can then create and add objects to it. In PyMunk, these objects are made up of a body and a shape. The body is what holds the physical properties of the object and allows us to determine its position on the screen. The shape is what the object looks like and will be used for collision. Together, these two components will make up all of the objects in our space. This process can then be repeated for different shapes. Now we can begin setting up PyMunk. So first of all, we need to make sure that we import the module. We'll say import PyMunk, and because we're working with PyMunk together with Pygame, we're going to import an additional module here, which is pymunk.pygame_util. This will allow us to use some features that will link the two libraries together. Now we create our PyMunk space. So underneath where I've currently got my game window, I will add another little section which will have the comment that says PyMunk space. And to create a space, we just assign it to a variable. So space is equal to pymunk.space with a capital S. Next, we want to start adding objects into this space. So for that, we'll create a function, and I'll add a comment to say function for creating balls. We'll define the function by saying def create_ball and add a few arguments, which will be radius and position. Then within this function, we will first of all create a body. So body is equal to pymunk.body with a capital B. And then we position this body. So body.position is going to be equal to this argument that we just passed through, which is position. In fact, I will just simplify this to pos and equate that to this variable here. But remember that PyMunk objects consist of two things, a body and a shape. So now that we've got the body created, we need to create the shape. Shape is equal to PyMunk. Well, these are going to be balls, so the shape that we want to use is a circle. And in here, we need to pass two arguments. The first argument is going to be the body that we assign the shape to. And the second argument, since this is a circle, we need to define its radius. And that is the other argument that we're passing through in this function. With that done, we can start assigning all sorts of physical properties to this object. We can say shape.mass is equal to 5. Now these are completely unitless, so you can pretty much just play around with the values and try and achieve something that looks and feels right within the game. So it doesn't matter if this is kilograms or pounds or tons, it's just a unitless value. For now, that's all we need. So with that done, we need to add this object into our space. So we'll call space.add, and we pass the body and the shape. So both of these objects will be added into our physics space, but I also need to return the shape back from this function. So let's go ahead and create a ball so we can test out this new function that we created. We'll say new_ball is equal to, we call the function createBall, and then we need to pass in those two arguments. For the radius, let's pass in a value of 25, for example. And then for the position, we need to pass in a tuple which will have the x and the y coordinates. So we'll just go with something like 300 and 100. So now let's run this code and see what happens. Well, it runs, it gives us the window as before, but there's nothing being displayed. So we're creating this ball, but it's not being shown on the screen. And this is because we aren't telling either Pygame or PyMunk to actually draw any of this on the screen. Now, if you remember, if I scroll up to the top, we imported this library here, pymunk.pygame_util. Now we can use this to draw the PyMunk objects on the screen. So if we go down to the section where we've got a comment to say PyMunk space, and we create our space just underneath it, we will add another line here that says draw_options are equal to pymunk.pygame_util.draw options. And then we pass in the argument here, which is our display window from Pygame, which we've created as screen up here. We can then use this to tell PyMunk to draw any of the shapes that we've created onto our game window. So we go into our game loop, and just at the bottom here underneath the event handler, we want to add in a couple of lines. So first of all, we add in our indentation to make sure that we're within this while loop, and then we'll say space.debug_draw, and we pass the argument that we just created, the draw_options. And underneath that, we want to call Pygame's own update function. So we say pygame.display.update. Now if we run this again, we see a little circle appearing. So this is the PyMunk object that we've just created using that function, and it's positioned at the coordinates that we've defined. So it's good in that we're able to display the image on the screen, or rather the object, but it's not actually doing anything. It's just a static object sitting there. So what we can do is go back into the space and apply some overall general parameters to it. The main one that we want to add is gravity. We go back into the section where we're creating the space, and just underneath the space definition, we will say space.gravity is equal to, and within here it's another tuple. We can define a horizontal and a vertical gravity. So the horizontal gravity I'll set to 0, and a vertical gravity I'll just set to, say, 5,000. Again, this is just an arbitrary value, it's unitless. So I'll run the code again, and nothing happens. So the ball should be dropping, but it just stays where it is. The reason for that is that the space is not being updated within the main game loop. So the space is initially created, and the ball is added to it, but then nothing else happens within this while loop. We need to tell PyMunk to update the calculations within the space, and we also need to define how often it does this. So we scroll back up to where we create the space, and just underneath I will add another comment to say clock. And within here I will set a frame rate. And the frame rate is going to be 120. This means we will update the screen 120 times per second. And just before we define this variable, we also want to create our clock. Say clock is equal to pygame.time.clock. Now we can use this clock and this FPS variable to do two things. We go down into the main game loop and we add another section here. First of all, we say clock.tick, and within here we pass in the argument or the variable FPS, which is our frames per second. This will then define and limit how frequently the overall game updates. Secondly, underneath that, we will say space.step, and within here we pass the inverse of that. So we say 1 divided by this frame rate. By linking these two functions with the same variable, we will ensure that at each iteration of the game loop, PyMunk will run all of the calculations, check for collisions, and update the positions of all the objects. We can now test this game again, and this time you can see that the physics have been applied and the ball starts to drop. Now we do end up with this tail here, but we can resolve that quite easily. We need to ensure that we're filling the background with some kind of background color so that we don't leave this trail behind the ball. So we go back up to where we're defining some of these variables, and underneath the clock we will add another section with a comment to say colors. And for now the only color that we need to define is background. So the background color I've just set to 50, 50 and 50. And these are RGB values, so it's red, green and blue. Then we go into the main game loop, and just after these two lines that we've just recently added, we will add another little comment here to say fill background. And the function is going to be screen.fill, and inside here we just pass the color that we've just defined, which is BG. If I run it again, you can see now the background has gone this kind of grayish color, and the ball now doesn't leave a trail, and you can see the ball just instantly drops off the screen. And we can play around with that by going back into this gravity and changing it to a different value. Now you can see it drops a lot slower. This is kind of what I meant by saying that these are unitless, so it doesn't really matter what you put in, you just need to make it look nice rather than trying to make it too real world and too scientific. But since our pool game is going to be a top-down game, we don't actually need gravity in this. So we can just go ahead and remove that. We'll go to this section here and remove this gravity. So now when we run it, the ball just stays where it is, stays stationary. What we're going to have instead is a cue ball that we can then shoot at different angles. Let's go ahead and create this cue ball. At the moment we've got this section where we're creating that one individual ball. Underneath that we'll create a cue ball. We will automate all of this eventually, but for now we'll just manually create these. Now the function is create ball, then we define the same radius, and then we need to give it X and Y coordinates. So let's move the cue ball over to the left hand side and put it at the same Y coordinate. And we run this again, and now we've got two balls. Now within PyMunk we can't differentiate between the two of them. When we come to drawing the images, we will know that this is the cue ball, and we'll draw the white image over it, and then this will be one of the other game balls. But as far as PyMunk is concerned, none of that really matters. They're just dynamic objects on the screen, and it will apply physics to them equally. Let's actually just move them down a little bit. So instead of 100 on the Y coordinate, let's make it 300. Yeah, so now they're a little bit more central on the screen. Now let's add a way of shooting the cue ball into the other ball. The way we'll do this is based on a mouse click. So as soon as I click the mouse, the cue ball is going to be fired to the left-hand side. So within this event handler, I'm going to add another event, and this is going to be event if event type is equal to pygame.mouse button down. So basically if we've clicked the mouse button, then we will shoot the cue ball. This can be done in a couple of ways. We can apply a force to the ball, or we can apply an impulse to it. For this application, impulse makes more sense. So we will call up the cue ball, and then we'll refer to the cue ball's body. Remember, it has a body and a shape. And then we'll apply an impulse to this body. And for that, we use the function apply impulse at local point. Within this function, we need to pass in a couple of arguments. The first one is a tuple, and this is going to be our impulse in the x direction and the impulse in the y direction. We want this to shoot over to the left-hand side, so it's only going to be an impulse in the x direction, and it will be negative. So let's just say minus 500, and then for the y direction, we put in 0. And the second argument is going to be another tuple, and this is going to be the x and y coordinates relative to the center of the body. Well, we want the impulse to be applied right in the middle of the body, so the coordinates are going to be 0, 0. Now let's run this code, and if I click, you can see this ball starts to move, and then it knocks into the other one, and they just slide along very slowly together. Now we can play around with this value here, so let's say 1500. This will apply a much stronger impulse, and it shoots the ball harder. Now you notice there we didn't have to code in any of the physics, we didn't have to do any collision checks or anything like that. We just apply impulses, apply forces, and PyMunk does all the rest. At the moment, those two balls are moving perfectly in line with each other, and that's because they are already in line with each other. So let's just move the cue ball down a little bit. Let's say we move it to coordinates 310 on the y-axis. So now this ball, it's hard to see, but it's actually a little bit further down on the screen. If I apply the impulse again, and you can see now the angles are coming into it as well. So because it's not hitting it directly straight on, it does go and bounce off at a slight angle. So already it's working quite well, but you can see that the balls just continue to move indefinitely. They don't seem to be slowing down. The reason for that is because they're floating in space. They aren't in contact with a ground or any kind of surface that we can then apply friction to. They're essentially free floating with nothing to slow them down. So what we need to do is add some kind of friction to them vertically. The way we're going to do this is by physically attaching or joining each of these balls to the space that we've created. This way they will slow down over time, and it will give us the impression of friction. To do that, we go to the top where we've defined our space, and just below that, we will say static underscore body is equal to space.static underscore body. So by creating a static body from our space, we can now connect the balls to the static body. And we will do that as soon as we create them, which happens within this create ball function. Now this next part I actually took from an existing example. I looked up the PyMunk website and I saw different demos there, and I looked at how they handled this top-down friction. So I copied this approach from there. And essentially what we do is we use this static object that we've created for the space, and we use the body that we've created for the ball, and we'll link the two together with a pivot joint. So we add a comment here to say use pivot joint to add friction. We create a pivot, and we say pivot is equal to PyMunk.pivot joint, and we pass in a few arguments. The first one is our static body, which is taken from the space, then the actual body, which is this PyMunk body we create for each of the balls, and then we add a couple of tuples, which are the coordinates where the joint is applied. So 0, 0 is going to be the center of each one. Then we define a couple of variables that we assign to this pivot. So pivot.max underscore bias is equal to 0, and we'll add a comment to say disable joint correction, and then we say pivot.max force is equal to 1000. Now you can play around with this value. The higher the value, the more friction. Emulate linear friction. So once this is created, we need to make sure that this pivot is added into our space using this function here. So at the end, we just add the pivot. Now if I run this again and I click, you'll notice now that we do actually have friction and the ball slows down by itself. Do it again, and now there's still friction. The balls come in contact, but then eventually they stop. The next thing we want to do is add in our pool table. So we go back up to the section here where we've defined our clock and the colors, and just underneath that we'll add another comment to say load images. We will assign this to variable table_image, and we'll use the function pygame.image.load. And in here we need to pass the location of our file. So in my case, the files are within this assets folder, and in there's a folder called images, and here where I've got all of the different ball images, the queue and the table. So this is the image that I want to load in. So we're going to be looking for the folder assets /images /table.png, and at the end we add .convert_alpha. And with this image loaded, we can now draw it on the screen. We go into our main game loop, and here we've got a section where we've got a clock and we've got this step. Then we fill in the background, and on top of that filled background we want to draw the pool table. I'll add a comment to say draw pool table, and we'll say screen.blit. The image we want to blit is our table image that we've just loaded, and then the coordinates are going to be the top left corner of our screen, which is coordinate 0, 0. So if I run this again, you can see now we've filled the whole screen with this pool table. But of course, just loading the image isn't enough. There's not really going to be any collision, it's just going to be visually there, but we can still go straight through it and off the screen. If we want to add some kind of collision between the balls and the pool table, we need to add these cushions in as PyMunk objects. Well, the way to do that is, if you remember, each object has a body and a shape. So that means that for the shape, we just need to pass in the coordinates that make up this shape here. And we'd repeat that for each of the 6 cushions. Now to do that, what I had to do was zoom in on the image and look at the pixel coordinate of each of these edges. So I've already worked that out, and you'll be able to just copy this from the source code for this video. But using that information, we can now create another function that will allow us to create each individual cushion as a PyMunk object. So we scroll back up to where we're creating the balls, and underneath this section where we create the new ball and the cue ball, we will add another space and create a function here, function for creating cushions. This will be very similar to this function above for creating the balls. So we'll say define create_cushion. And for now, we won't pass anything in, but we will come back and add an argument later. We first of all need to create a body. So we'll say body is equal to PyMunk.body. And then within the brackets here, we need to specify the body type. We'll say body_type is equal to PyMunk.body.static, all caps. Now we didn't have to do this when we created the balls here. We just left it with empty brackets. By default, that created dynamic bodies, which meant that they can move around and bounce off each other and have collision. Here, we don't really want the body of these cushions to be able to move around. We want them to just be static objects that are there purely for collision so that the balls can bounce off of them. To ensure that happens, we add this parameter here. The next thing we need to do is define the position of the body. We say body.position is equal to, and we'll just set this at 0, 0. So that's the body defined, but remember we also need to create a shape that we attach to this body. So we'll say shape is equal to PyMunk, and this time it's going to be a polygon. So it's PyMunk.poly. First argument is the body that we attach this shape onto, and the second argument is going to be the set of dimensions or set of coordinates that this polygon is going to be drawn through. Now this is going to be different for each cushion, so this is going to be the argument that we pass through in this function. So let's add that in now. We'll name this argument poly_dims, and we'll pass it into this shape. And once the body and shape are created, we need to make sure that we add them into our space. We'll say space.add body and shape. The next thing we need to do is actually define all of these polygon dimensions. Well, like I said, I've already gone through the image and I've picked out the corner coordinates of each of the cushions. So to save us typing it all out again, I'm just going to paste them in here. We'll paste them just above this function, and I need to make sure that I close that bracket there. So a comment here to say create pool table cushions, and for now I've just put in one single list. So this will comprise just one cushion. These are the 4 coordinate positions that will create that cushion. So the polygon function, or this create cushion function, is just going to take each of these points and it will draw a line through them. This is going to envelop it and create one complete polygon. So with our list of coordinates created and our function defined, let's now call the function to create these cushions. We'll say for C in cushions, which is this list up here. At the moment, it just has one list entry within it, but we'll add to that. So for C within that list, we want to run our function, which is create cushion, and we want to pass C, which is this list of coordinates, into the function. Now, before we run this code, I've noticed there's a little typo up here. So this should be just static, not statics. So we'll delete that S and we'll run the code again. And now you can see we've got the image as before and we've got the cushions, but notice that this one is a different color to the rest. That's because this is actually the PyMunk object. This is the first cushion that's now been created. And essentially, because I've worked out the coordinates of each of the corners, it's perfectly overlain on top of the existing image cushion. In fact, if I go and comment out this blit function here to hide the table, you can see the cushion is still there. It's an object that is created within PyMunk. So now we'll add this image back in, and what we can do is go into this cushions list and add in all the remaining ones. I'm just going to copy them over, and you can do the same. You can just copy them from the source code rather than having to watch me type them all out. So these are the 6 cushion coordinates. So let's run this again just to test it. And we can now see we've got a cushion, or rather a PyMunk object polygon at each of the positions of the cushions. So if I was to hide the table again, just comment this line out, we'll see what's left. We'll see what's going on behind the scenes. So this is going to take care of all of our collisions. We don't really need to worry about coding all of that in because PyMunk's going to do it for us. So let's add the image back in so it looks a bit better. Now let's test out this collision. So if we just start shooting this ball over very slowly until it makes contact, and there we go. We've got a collision and it's stopped. It's not going through. It hasn't bounced off, but that's okay. That's deliberate. We just haven't gotten that far yet. But we can see now that the ball is being stopped by this cushion here. And if I keep trying to shoot it through, it can't. It bounces into it, but it's got nowhere to go. So now let's fix the issue of the ball not bouncing off the object. PyMunk by default doesn't know whether the objects need to be sticky or bouncy, whether they should be smooth or if there should be a lot of friction. We need to define all of these parameters as we create the objects. So if we go back into both of these functions, so first of all, the create ball function, here we've defined the mass for the shape. Well, just underneath that, let's also say shape.elasticity, and we'll set this to 0.8. Then we will go into our cushions function here and do the exact same thing. So once we define our shape, we'll say shape.elasticity is equal to 0.8. Now let's run this again, and we'll shoot this ball over. And now you can see, not only did this ball bounce further than it did before, because these balls now both have elasticity, but when this came in contact with the wall here, with the cushion, it bounced off it. So now we've kind of fixed that problem of the objects just sticking to each other. They're actually bouncing off properly. Now let's create all of the remaining pool balls properly. To start with, we need to define an additional variable. If we go back up to where we're creating these current balls, we pass in this first argument, which is our radius. We don't want to do that manually. We can just define a variable that's going to control this for us. So we go to the top of our code, and just up here where we've defined our clock, underneath that I will add another section which will be called game variables. And the only variable I need for the time being is the diameter of the balls. So I'm just going to shorten this to the first 3 letters, and I will set this to 36 pixels. That's just how big the images are. Now we can go to the section where we're creating them manually, and we can automate this part. So we'll keep it there for now, and then we'll delete it as we go. So we'll add a comment here to say set up game balls, and we're going to store all these inside a list. I'll create an empty list first of all. On a pool table, the balls are set up in a triangle. We're going to treat this as a grid with rows and columns, but as you move through the columns, the number of balls in the row reduces by 1. So by the end of this for loop iteration, we're going to end up with a pyramid shape. Let's define our starting number of rows, which will be 5. We will separate the potting balls from the cue ball. So we're going to set up the potting balls first. I'll add a comment here to explain that. So we'll say potting balls, and then we will create our for loops. The first one is going to be the columns. I'll say for call in range 5, so that we can iterate through 5 columns. And in each column, we want to iterate through the rows for row in range rows. This will begin by taking this rows variable of 5, but as we go through this for loop, we will reduce this for each column. Now we can take this new ball variable here and actually move it into our for loop. We'll indent it, and then we can just start changing the arguments in here. So the first argument is the radius. We can now remove this and replace it with the diameter variable we created earlier and divide it by 2, because radius is just diameter over 2. Next, we need to define the x and y coordinate of each of these balls. So we're going to create that as a separate variable above, which will be pos for position. We'll start off with the x coordinate. We'll offset all of them by 250 pixels from the left. And then we will use our call variable as we move through this for loop, multiplied by the diameter variable for the balls. So as we go through the columns, we will then arrange each column next to the one before it using this diameter. So that takes care of the x coordinate. Now we can do the exact same thing for the y coordinate. We'll offset by 267 pixels from the top, and we add row multiplied by diameter. And now that we have this pos variable defined, we can replace the second argument here with pos. Once this new ball is created, we can now add it into this balls list. And we can just do that by calling the append function and passing through the new ball. Now the important part here is once we've finished this full iteration, we've moved through all of the rows, we then move on to the next column. At that point, we need to make sure that we reduce the number of rows in the subsequent column. So we say rows, subtract 1. Make sure that this is indented correctly. So it needs to be in line with this for loop, not indented inside it. That takes care of all the potting balls. So now let's add a little comment here to say cue ball. And we're going to do the same thing. We'll define a pos variable for it first of all, and this will be a little bit easier. It's just going to be a fixed value. So the x coordinate I've already worked out is 888, and the y coordinate is going to be the middle of our screen. So we say screen height divided by 2. Then we create the ball in the same way. We change this first argument to diameter divided by 2, and then the second argument just becomes the new pos variable. And once that cue ball is created, we need to make sure that we append it to our list. So we call the append function and we pass in the cue ball. Now let's run this code and see what happens. Okay, so now you can see we've got the cue ball positioned in the right place, and we've got sort of a pyramid thing going on here, but it's not quite correct. We've got the right number of balls in each column, but they're being laid out all in line with each other. What should actually be happening is that each column is slightly staggered in between the one before it. So we just need to fix this little bit here. The way we do it is by adding an additional offset to this pos variable within the for loops. So right at the end where we've got the y coordinate being defined, we just add another offset. And this one is going to be dependent on our column. So it depends on which column we're currently in. As we move through the columns, we want to add an additional little bit onto the y offset. And this will be column multiplied by the diameter of the balls divided by 2, rather the radius. Run this again, and now you can see they're nicely stacked up in the right order. The only thing is they're maybe a little bit too close to each other, so they're almost overlapping at this point. There's no gap between them at all. We want to add just 1 pixel in between all the balls to space them out a little bit. So in the x coordinate in this section here, we just want to wrap this diameter variable in another set of brackets, and then we add +1 to it. And then we'll do the same thing to this one on the y coordinate. So we'll wrap this in another set of brackets, and we'll add +1 to it. Run it again, and now the balls are spaced out with a tiny little gap in between them all. And we can test this out by firing the cue ball into them. So you can see that they all just start bouncing off each other. There's physics and collision working on each individual ball. Well, the next thing to do is to add some of the images, because right now we don't have anything to show which ball is which. So at this point, it's hard to track which one is the cue ball. We can only tell once we click and the cue ball starts to move. So let's load in all of the images for each ball first of all. We go back up to where we're currently loading our table image right here. And just underneath that, we will create an empty list, which will be ball_images. We'll set that to an empty list. And then we're just going to iterate through the number of images that we've got. So if I open up the panel and I can see the images that I've got here, it goes from ball_1 all the way through to ball_16. So we can just load them all in automatically with a for loop. All we need to do is control this variable that controls the number. If the file names go from 1 to 16, that means that our loop needs to be for I in range 1 to 17. Because remember, the second variable within this range is not inclusive. So we go up to, but not including 17. And then we just load the image. We'll say ball image is equal to pygame.image.load. And in here, we need to pass the location of the file, just in the same way as we did when we loaded the table. Well, it's in the same folder. It's in assets /images, and then it's called ball underscore and then some kind of number. So we'll come back to this, but let's for now just put ball1.png. And at the end, we need to add convert alpha. Once the image is loaded, we need to make sure to add it into our list. So we'll call the append function and add this new image into it. Now we're left with two lists. We've got one list of the images, and then we have another list here of the ball objects. They've both got the same number of items inside them, so that means that each ball object within this list can be corresponding to a particular ball image within this list. So to draw them, we go down into our main game loop, and underneath where we're drawing the pool table, we will add another little section here to say draw pool balls. What we'll do here is have a for loop, which is going to iterate through each of the balls within the balls list. So that's the objects, the PyMunk objects, rather than the images. Instead of I'm going to call this ball. So for ball in balls, we then want to draw the image. So screen.blit. And what image are we calling? Well, we've got our ball images list, and we just need to access the correct index. Well, that means that we need a counter for this for loop. So as we iterate through them, we need to count how far we've gone. And we're going to do this by adding a second variable into this for loop. We'll say for I, comma, ball, and then we will wrap this in enumerate. So now, as well as iterating through this list and going through each of the objects, it will also keep count within this for variable. And we can demonstrate this. If we print ball in here, and I'll just comment this part out because it's not complete, and run this code, you can see that it's going through that list and it's giving us the PyMunk objects. So it gives us the shape of a circle at each object within this list. Now if I replace this with I and run it again, we now just get numbers. So now it's counting. It's going through each of the items within it and assigning it a number. So 0, 1, 2, 3, 4, 5, and just counts up the way. So we can use this I variable to work through our ball images list and pull out the images accordingly. So let's go back to this and just complete this. So we'll put I in here, and then the second argument needs to be the X and Y coordinates. Well, that we can just take from the PyMunk object. We can say ball.body.position. So let's run this and see what happens. Okay, so it's kind of worked, but you notice that all of the images, they seem to be offset down and to the right from the PyMunk objects. The reason for that is the PyMunk position coordinates are based around the center of the object. However, when we blit an image in Pygame, it uses the top left coordinates as 0, 0. So in this case, it's basically just taking, it's taken the ball image and it's taken its top left corner and put it at the center of the PyMunk ball object. So we actually need to offset each of these images to the left and up accordingly. We're going to break this part into two. So we'll add another set of brackets here, and we'll split this up into our X and Y coordinates. So the X coordinate will be at index 0, and then the Y coordinate is going to be the same thing, but at index 1. So if I run this again, nothing should change. I still have the balls positioned, or the images positioned in the wrong place, but we've now split this up into two components, the X and the Y component. Well, we know that they both just need to be moved left and up, so they need to be reduced by the radius of these balls. So we can say ball.radius, and it will take the radius from the PyMunk object. We do the same thing here, subtract this, and if we run this again, Now you can see, well, you can't actually see the images anymore, but they're all lined up underneath the PyMunk objects. If we temporarily hide them here, we'll be able to see them poking through underneath. So that's working pretty well. We've managed to load all of the images and we're displaying them all in the right place. And as we knock about, all the balls move, so do the images. But of course, you would have noticed that they all look exactly the same. We've just got every single one with the number 1 on it. Well, that's because of the way we've loaded them in. So if we go back up to the top where I loaded these images, although I added this loop, each time it iterates, it just loads this same image in for us. What we need to do is, rather than typing this number in here, we need to replace this with the variable so that each iteration of this for loop, that I variable goes in here. And we can do this with string formatting within Python. So right at the beginning, before our quotation marks, we add an F, and then this part gets replaced instead with curly brackets. So whatever goes inside the curly brackets is going to be a variable that will get added into this string. And we just put I in there. So this for loop counter is now going to be added in here. And if we run this again, we won't see the images because they're going to be hidden underneath the PyMunk objects. So I'm just going to comment this section out for a second, run it again, and now we can see all of the balls are set up here correctly, and we've got the cue ball on the right hand side as well. The next thing we want to add is the actual cue itself, so that we can aim properly and shoot the ball in the right direction. So we go right up to the top where we're loading all of our other images here. And before we load the table image, let's load in the cue image. We'll say cue_image is equal to pygame.image.load. And then we pass in the file name. In fact, I'm just going to copy it across from the one below because it's essentially the same thing. We just need to change from table.png to cue.png. The cue isn't going to be a PyMunk object. It's not going to be related to it. It's just a visual that we want to be able to show within Pygame. To create the cue, we're going to use a class. So we'll go down underneath where we're creating our cushions, and just before the game loop, we will add a little section here, and I'll add a note to say create pool cue. We'll create this as a class. We'll call it class cue, and it doesn't need to take any arguments in here. Then we start with the constructor, which is our init method. For the init method, we add the self argument and we add the position argument. So for now, that's all we need. It will allow us to position the cue relative to the cue ball. For this cue, all we need is the image and then a rectangle based on that image. That will allow me to position it on the screen correctly. I will say self.image is equal to the cue_image that I've just loaded in. And then I can create a rectangle from this by saying self.rect is equal to self.image.get_rect for rectangle. Lastly, I can position this cue based on the position coordinates that I'm passing through. I will say self.rect.center is equal to pause. And pause is this argument that we're passing through here. Normally, this would be all that we would need to create this. However, this cue is going to be rotating, so we'll rotate this around the cue ball to allow us to aim, which actually means we need to add another argument here. So above self.image, we will say self.angle, and we will set that to 0. And when it comes to rotating images within Pygame, we need to preserve the original image. So that means that we need to create one more argument here, or rather one more variable, which is going to be self.original image. And it's this that we set to our cue image. So our original image variable is always going to be the cue image that we load in. We have our angle defined. That means that this image variable is actually going to be changing depending on the angle. So rather than setting it to the image here, we will transform it. So we will rotate it to begin with. We will say pygame.transform.rotate. And what do we rotate? Well, it's the original image, and we rotate it by the angle of self.angle. So then the rest stays the same. We create a rectangle based on this self.image, and at the moment the angle is 0 anyway. So our self.image is going to be the same as the original image. However, as the game goes on and we rotate the cue around the cue ball, this angle is going to change and this image will change with it. But this original image is always going to stay the same. This will give us our reference at all times. Before we go too much further, let's just create an instance of this cue class, and we'll do it just underneath here. We'll say Q is equal to an instance of the Q class. And then we need to add in the arguments required. So the argument here is pos. We need to pass in the position where we want this Q to be created at. Well, the Q is always going to be placed around the Q ball. Now, if we go back to where we created the balls up here, we placed them all into this list. And the last object that we put into the list was our Q ball. So if we just access this balls list and we look at the last item within it, we'll be able to get the position of the Q ball. So we go back down to where we create our Q, and for the position, we call up that list, and we go to the last index. To get the last index, we just put in -1. So that will pull through that PyMunk object. We need that body position, so we type body.position. Let's run this and just see if it works. Okay, so we didn't get any errors. We don't see the Q yet because we're not drawing it, but we know that it's being created there in the background. Now we can create an additional method within this Q class, and that's going to be the draw method. We'll say def draw, and here we pass in the self argument as always, and then the surface. Surface is going to be whichever whichever screen we want to display this onto. Now before we actually draw anything on, we need to update our image based on the angle. So we haven't added in the code for changing the angle yet, but eventually we will have another method here that will take care of the angle. So we need to make sure that we update self.image before we blit it. So we can just copy this line down. We put this into this draw method as well, and it means that if the angle does change, as soon as we call the draw method, it will recreate the self.image variable for us based on the new angle. And now we can blit this image onto the screen. We can say surface.blit. We're blitting self.image, and the location is going to be self.rect. With this defined, we can now call the draw method within our game loop. So just down here below the draw pool balls section, we're going to draw the Q. We'll add a comment to say draw pool Q, and we'll call the Q method. We'll call the draw method. Now this takes one argument, which is the surface. So we'll pass screen into here as our game surface. We run it again, and there we go. Now we can see the Q ball, or the Q coming up behind the Q ball. Of course, at the moment, it's not able to rotate. It's just sitting there as a stationary image. So let's add the other method that allows us to update the angle. So above the draw method, we will create another one, and we'll call this update. Say def update. It takes the argument of self, and then it takes the argument of angle. And all we're doing here is just changing this self.angle variable to whatever the new angle is. So anytime we call this update method, we pass in the new angle, and it will update this variable within it. Then we call the draw method, and it will recreate our self.image variable based on the angle. What we need to do now is work out the angle that we need to position the Q at. And for that, we're going to need some trigonometry. So we need to import an additional module. We go all the way to the top, and we say import math. We can then go back down to where we're drawing the Q within the main game loop, just within this section here, and we can add a little bit of code before it. I'll add a comment here to say calculate pool Q angle. And the angle is going to be based on the mouse position. So whatever we place the mouse relative to the Q ball, we want the angle to be put on the other side of that. So if I put the mouse over here, then the Q is in the correct position. But if I move the mouse over here above the Q ball, I want this Q to rotate clockwise around here, so it's pointing at it from below. That way, wherever I'm pointing the mouse, that's where the Q is going to be shooting the ball at. Well, to do that, we need to work out, first of all, where the mouse is positioned on the screen. So we take mouse_pos is equal to pygame.mouse.get_pos, and that will return the X and Y coordinates on the screen of the mouse cursor. Then we work out the horizontal distance between the mouse position and the Q ball, and we do the same for the vertical distance. We'll say X_dist is equal to, now remember that the Q ball is the last index position in this list, so we type -1 to get the Q ball, and we access the body, and from there we can take the position. Now we just need the X coordinate, so we access index 0. And then from that we subtract our mouse position, and again it's the X coordinate we're interested here, so it's going to be index 0. And we can just repeat this again, so I'll copy it down, and we change it to Y distance is equal to the same position, so it's going to be the Q ball, but it's going to be index 1 and the mouse position index 1 as well. The only difference between the X and Y here that we have to be mindful of is that the Y coordinate increases as you move down the screen. So the Y coordinate is kind of flipped in Pygame. That means that we need to invert this variable. We'll wrap the whole thing in brackets and we add a minus sign at the start. So that will make sure that it comes back negative. Or rather, it will just invert whatever it is. So if it's already negative, it will make it positive. And just to add a reminder for that, I'll add a little comment here to say it's negative because Pygame Y coordinates increase down the screen. Now that we have our X and Y distance, we can work out the angle using some trigonometry. Now I'm not going to go into how this works out. I'm just going to type out the equation that I use for it. Q angle is equal to math.degrees of math.a tan 2, and we pass in the y distance and the x distance. So we use these two distances, we pass it through into the arctan function here to give us an angle in radians, which is why we then wrap it within this function here, which converts the radians into degrees. Now we can take this Q angle, which has now been converted into degrees, and pass it back into our update method. We can call q.update and pass the Q angle. So if we run this again, we now have our Q. It is rotating, but you can see it's doing something very strange. It's not quite working. Apart from some positions like this 0 coordinate here, it's perfectly horizontal, but as we move around, it seems to go away with it until we get back to the other side. If we go back into the draw method here for the Q and draw the rectangle as well as the image, it might help us visualize what's going on. So underneath this surface.blit function, we'll say pygame.draw.rect, and then we pass the surface a color, which we'll just define here temporarily as 25500 for red, and then the rectangle, which will be self.rect. So if we run this again, you can now see the rectangle here coming up. Now you can see that this rectangle is much bigger than the Q itself. The reason for that is the image that I've used for the Q is actually a lot longer. So the Q is offset from its center. And I can demonstrate that if I open up the image. So if I go into our assets folder and open the Q, you can see the Q starts over there. That's the tip of it, but the actual image is quite a lot wider. It's just the rest of it is transparent. Now this is done deliberately, is to allow us to rotate the Q around the center point, but it does mean that we need to slightly alter the code for drawing it on the screen. So I'll hide the panel and I'll get rid of this rectangle because we don't need it. And I'm just going to change this section here of the surface.blit function. So after this comma, I'm going to break it down over a few lines and I will manually add X and Y coordinates for it. So we'll add another bracket here. And the X coordinate is going to be self.rect.center X minus self.image.get_width divided by 2. So that takes care of the X coordinate, and then we do the same thing for the Y coordinate. So it's going to be self.rect.center Y minus self.image.getHeight over 2. And I just need to double check my brackets here because I think I've got too many. So we don't need this one here and we don't need this one here because this essentially is a tuple here. So this contains our X and Y coordinates within one set of brackets. Okay, so let's run this again. And now you can see we're rotating perfectly around the cue ball. So now let's try and take a shot with the cue ball positioned. Okay, so the cue moves over here, but the cue ball is still stuck on this side. Not only that, but the angle is messed up because it's trying to change the angle based on where the cue ball is. So if I keep shooting, the cue just stays exactly where it is. Okay, so we need to reposition this every time the cue ball moves. We can go back into the main game loop where we're currently drawing the cue, and here is where we work out all the positions anyway. So once we work out the mouse position, just after that, we can reposition the cube. We can say q.rect.center is equal to, well, the center is always going to follow the cue ball itself. So we can access that again at index -1. And from there we can take the body and the body's position. So now, after we take a shot, the cue moves with it. Now, of course, the Q should really disappear while the ball is moving. We'll get to all that, but for now we can see that the Q is properly repositioned based on wherever the cue ball goes. Now we can add a few improvements to how the cue works. First of all, we want to hide the cue whenever the balls are in motion. For that, we're going to add an additional trigger. We go all the way up to the top where we're defining our game variables in here. And underneath the diameter, we will add another one, which will be called taking_shot. And to begin with, we will set this to a true value. What we can now do is use this variable as an if statement check to then draw our cue. We go back down into the main game loop and look for the section where we're drawing the cue, which is here. So the cue update and the cue draw, all of this here is happening all of the time. But we only need this to run when we're setting up a shot. So we can wrap all of this inside an if statement. We say if taking_shot is equal to true, and then we indent everything that's within there. So we will only display the cue and we'll only calculate the angles and so on as long as we are taking a shot. But at the moment we have no way of setting this variable to false. So that means that this code is always going to be run. We're always going to display the cue regardless. What we want to do is take a shot and then wait until all of the balls have stopped moving again before we take the next shot. That means we need to add a check to see if any of the balls are still moving. So just above where we've got this comment for drawing the pool cue, we'll add another section with a comment to say check if all the balls have stopped moving. And the way we'll do this is we will first of all assume that we are taking a shot. So we'll set the variable taking a shot to true, and then we will iterate through each of the balls in that list. So we'll say for ball in balls, which is the list of PyMunk objects, and we'll check each of their velocities. We can add an if statement here to say if ball.body.velocity, and we will access index 0, so this is the x velocity across the screen left and right. If that is not equal to 0, that is one condition. Alternatively, we check for the same but in the up and down direction, so the y coordinate or the y velocity, which is at index 1. If either of these conditions are met for any of the balls within that list, well then that means that the balls have not come to a stop, and so we're not ready to take a shot yet. And we can set this variable, taking shot, to false. So let's test this out. We run the game, we take a shot, and the pool cue disappears. Now the ball stops, and it reappears again. And we can keep doing this, and keep taking shots. Every time everything stops, the pool cue reappears. We can, however, run into a slight bug with this code, which is that when the ball velocity is not exactly 0, but let's say it gets stuck on a very, very low number like 0.000001, well, this condition will not be true, but as far as PyMunk is concerned and the physics are concerned, the balls are pretty much stopped. So what we want to do is wrap this inside an int function. This will convert the float value into an integer. So if we are in a position where we are very, very close to 0 but not quite at 0, converting it to an integer will take it to a 0 value. So we do the exact same thing with the second check here. Oh, I realized I missed out a part there. So this should say is not equal to 0. It would still work if we missed this out as before. It's essentially the same thing. It's just checking that this is a non-zero value, but I like to type it out so it's more explicitly stated. The next thing we want to do, and the more important thing, is to be able to actually aim the direction in which the cue ball is shot. So at the moment, no matter where I aim, it still just moves to the left. And that's simply because of the way that we've set up the shooting code. So down here, whenever the mouse button is clicked, we just apply an impulse and it's already fixed. So it's fixed to have this X direction impulse. There's nothing in the Y direction. We don't want this to be fixed. We want this to be based on the angle that the cue is pointing at. So we're going to use a little bit of trigonometry here, and we will break down this angle into its X and Y component. So in this section here, we're just going to expand it a little bit, and we will say x_impulse is equal to math.cos for cosine of the angle that the cue is pointing at, which is the variable q_angle. However, we need to convert this angle back into radians before we can apply this cosine function to it. So we need to wrap this in another set of brackets here and say math.radians. So we convert this angle into radians and then we take the cosine of it. This will give us the x component, We can then do the exact same thing for the y component. We copy that down, change this to y impulse, and now instead of cosine, it changes to sine. We can update this last line as well. Now, we previously just called this function on the cue ball because we do create the object as that. However, seeing as now we've created everything and added it into a larger list, which is this balls list here that contains all of the individual PyMunk objects, we know that the very last entry in that list is the cue ball. So rather than calling it specifically here, we will change this, we'll access the list, and we will access an index -1, which will give us the last value, the last object, which was the cue ball. Now we can replace this fixed x and y impulse here. So we will change this one, and we'll replace it with our x_impulse value, and then we'll do the same for the y impulse. However, these are just the components of our angle, so I actually want to multiply this by an overall force. We haven't defined this variable yet, we'll do that in a second, but we will add force multiplied by these impulses. This will then allow us to change the power on the cue depending on how hard we want to hit the cue ball. So let's go to the top where we're defining our game variables again, and now we add another one here just underneath the diameter, which will be force. So for now, again, we'll fix this value. So we'll just set this to, say, 2000. And if we test this again, so let's try and shoot up the way. And there we go. It works fine this way. Now let's go left and right. Oh, it's going the wrong way. And this is just because of the way the angle is worked out. It's calculating it based on the fact that I'm pointing to the opposite side of the cue ball from where the cue is. So all I need to do here, you notice if I shoot right, it goes left. If I shoot left, it goes right. It just always goes in the direction of the cue. I just need to invert that variable. We go back down to this section here, and for this one, we just add a little minus sign to the x impulse. Try it again, and now it goes in the correct direction. But right now, that force is fixed, so we always just hit the cue ball with the same power each time. Sometimes we want to be able to hit it harder, sometimes we want to be able to just tap it. Well, that means we need a way of controlling this force. So let's go all the way back up to where we define our game variables. And underneath taking shot, we will add another one, which will be powering_up. And we'll set this to false to begin with, because we're not powering up, we're just taking a shot, we're just setting up. And the way this will work is that as long as we hold the mouse button down, we're going to be powering up. And then as soon as we let go, that's when we stop powering up and we take a shot. So we need to alter this code down here a little bit within the event handler. We'll say that if the mouse button has been clicked and taking shot is equal to true, then powering up becomes true. And then we need the same check, but for when we let go of the mouse button. So we just want to copy this down, paste it underneath, and we will move all this code in a second. I'll just make some space for it here, just to space it out. So now the event type is going to be, instead of mouse button down, it's mouse button up. And taking shot is true, so we're still in the same condition. Well, now powering up is false. So this is essentially our trigger. So as long as we hold the mouse button down, we start powering up. And as soon as we let go of the mouse button, we stop powering up and we take a shot. Well, now we need to do something with these triggers. So we're going to copy this code out of here. We'll cut it out of there, and we'll move it to another section just above. We've got this section up here for drawing the pull cue. Well, let's add another bit underneath with its own comment to say power up pull cue. And the check that we're going to have here is, first of all, the trigger. So if powering up is equal to true, then we want to increase the force. So for now, we'll just add a pass in here and a comment to say increase force variable. And then we add an else statement, or rather, let's go with an elif. So elif powering up is equal to false, and taking shot is equal to true. So this means that we are in the process of taking a shot, but we have just stopped powering up. That means we've let go of the mouse button and we're ready to essentially fire off the shot. Well, in that case, this is where we paste all of that code that we just cut. So this is the point at which we would calculate our impulses, and we will calculate the force at which we want to apply that impulse. Let's just make sure the indentation here is correct. There we go. And as soon as that's done, the force variable which we haven't actually done anything with yet, but the force variable resets back to 0. So that means on our next shot, this section here is going to be run, we'll increase the force variable, then we'll let go, and we'll reset it back to 0. So now let's add a way of updating the force, or rather increasing the force variable. Let's go back to where we defined it first of all, because we've already set it to 2000. Let's set that to 0. And now go back into this section with the if statement. We'll remove the pass and we'll remove the comment. And instead, we will just add numbers to this force variable. So we'll increase this force variable by, let's say, 100. So as long as we hold it, it will increase by 100. And for the time being, we don't have a visual display of this force, so let's just print it out. We'll print force. So we'll be able to keep track of it down here in the console. So if I click the mouse button and hold it, you can see it's shooting up really quickly, and as soon as I let go, it fires through really hard against all these. Now if I just tap it, it just goes really lightly, because as soon as we take a shot, it resets force back to 0. So as long as I tap it, it just goes really lightly, or I can hold it to charge it right up, and smack that ball really hard. Now you may have noticed a little bit of a problem there. I hit the ball way too hard, and essentially it was too much for the PyMunk engine to handle. It went through the collision, it went through too quickly. And that's referred to as tunneling. So if an object moves so fast that it passes through something in between two different frames, well then the collision is never detected. So it just goes straight through and it's off. So what does that mean for us? Well, we want to make sure that we limit this force to a reasonable value, so that you can't just hold the mouse button forever and charge it up to a silly amount. It needs to go up and then come back down again. So we're going to define a couple more variables. Let's go back up to the top of the code here, to this game variables section. Underneath the force, we will define a max force. So we want to add a ceiling to this that we can't exceed. And 10,000 is going to be more than enough for this. You can play around with this, but I found this is a decent value for this game. The other thing we want is the force direction. So first of all, we'll just set this to 1, and then I'll show you what we're going to do with this variable. So we go back down to the code where we're checking for the shot and we're powering it up, which is down here. And this section here where we increase the force by 100, we'll multiply this 100 by the force direction. This variable is already defined as 1, so that means that it's not really going to change what we had before. It's just going to be force plus 100 each time. But what we then want to do is add a little if statement underneath. If force is greater than or equal to the maximum force, so if it goes to that limit, or force is less than or equal to 0, then we will flip this direction. So we'll say force underscore direction is multiplied by -1. Now let's run this and see what difference it makes. So keep an eye on the terminal down here. So as I hold the mouse button down, you can see that the force value increases to about 10,000, which is our max, and then it drops back down to 0. So now I can adjust the shot power as long as I want. Basically, I just change how long I hold the mouse button down for, and it will oscillate between those two values. So if I want to take a powerful shot, I'll just wait and release when it's close to a high value. You can see here that it was decreasing, so it was going down rather than up. Now, if I go to take another shot, oh, we're a bit stuck. So we're stuck between 0 and -100. That's because at that point, the force direction was still -1. We were coming down the way. So this code here starts with force is 0 because we reset it when we let go of the mouse button. And then it tries to subtract 100 from it because it says 100 multiplied by -1. So then this condition is instantly met and we just get stuck in this little loop here where the force direction keeps flipping between 1 and -1 and the force oscillates between 0 and -100. To fix that, all we need to do is just add another little reset here, which is force direction is reset back to 1. So now we can test this out again, and I'll just power it up, wait until it's starting to come back down, take a shot, and now I should be able to take another shot without any problems. There we go. Okay, so that's working well. However, we don't really want to be displaying the force down here as a value. What we want is some kind of visual feedback for the player so they can see how far they've powered up the cue ball. And what we'll do for that is just create little power bars. We're not going to use any images, we'll just create little red rectangles. So let's go back up to the top of the code where we're loading in the images and creating everything, just above the main game loop, so somewhere around here. So after we've created the cue, let's add a little space here, add a comment to say create power bars to show how hard the cue ball will be hit. We'll create a variable which will be power bar, and then we can create a Pygame surface. We'll call pygame.surface, and in here we just need to pass in x and y coordinates, or rather width and a height, sorry. So for the width I'll set 10 pixels, and for the height I'll set 20 pixels. I want these power bars to be red, so that means that I need to fill the surface with a red color. We'll say power_bar.fill, just the same way as we did with the background of our screen. We can fill this with any color we like. Now I haven't defined red yet, so I'm going to type in red, but I'll need to go back up to where I'm defining my colors, which should be somewhere here. Yep. So underneath the background, I will define a color red. And remember, these are RGB values, so it's 255 for red, and then it's 0 and 0 for green and blue. Now that these power bars are created, I can go down and actually draw them on the screen. So we go back into the main game loop, and just into the section where we were powering up the cue here, we will delete this print statement. We don't need to output the actual value. We're going to represent it with these power bars. And then I'll make sure the indentation is correct. So we should be inside this first if statement, but not inside the second one. So it'll be in line with this one. We'll add a comment to say draw power bars. And the number of bars is going to depend on the value of this force variable. So the higher the force, the more bars. I want each bar to represent 2000 of force. So basically when we reach 10,000, well, that's when we've got all 5 power bars. And then every time before that is going to be 2000 per each bar. So I'm going to use a for loop here. I'll say for B for bar, for B in range. And this range is going to be my force value divided by 2000. Oops, 2000. But of course this could mean that I end up with a float value here. So what I'm going to do is round this by calling math.ceil for ceiling. And this will allow me to round these values. Then I can draw each individual power bar on the screen. I'll say screen.blit. The image or surface that I want to blit is the power bar that we just created. Then I need to define the x and the y coordinates for this. Well, both of these need to be relative to where the cue ball is. So for the x coordinate, we know that the cue ball is just the last entry within this list. So we access it by going to index -1, and then we call body.position at index 0. That will give us the x coordinate of the cue ball. And then each bar that's drawn, it needs to be drawn to the right of the one before it. So actually, as we iterate through this variable here, or rather through this for loop with the variable b, we need to adjust the x coordinate each time. So in here, we just add plus b multiplied by 15. And then we can repeat this for the y coordinate. So we just copy this section here, add a comma, and add our y coordinate. I think I'm going to have to split this up over a couple of lines because it's getting a bit too long for the screen. So let's just break it after this comma. So that's our x coordinate, and we break that one. That's going to be our y coordinate. So we can then update this to, it still takes the same ball, it needs to be the cue ball, but now it's position index 1, which is the y coordinate, and we don't need this offset here, as in we don't need it controlled based on a variable. We do still need an offset of some kind. So we're going to offset it by 30 pixels below the cue ball. So let's run this and see how it works. So I'll hold down the mouse button, and you can see the little power bars appearing. They fill up all the way to 5, which is our 10,000, and then they drop away again. So let's just see if that works. I'll release when it's close to the end. Yeah, and it goes pretty powerfully. And then I release it when it's just close to the bottom, and it just taps it. So it's working well, but you'll notice that the bars are actually starting right underneath the center of the cue ball. We just want them to be offset to the left a little bit so that they kind of line up nicely underneath it. That means we just need to add an offset to our x coordinate here. And that is going to be a -30. So before we add this b times 15, we just subtract 30 from the starting value. Try this again. And there we go, that's a lot better. So now they look like they're lined up more or less just underneath the center of the cue ball. The next thing we're going to do is add a way of checking whether a ball has been potted. To do this, we're going to have to set up pockets at each of these 6 locations. We're not going to use PyMunk or any fancy physics for this. We will just figure out where their coordinates are and then check when one of the balls comes in close contact with it. So we need to set up a couple of variables first. Let's go to the top where we define our game variables, just down here. So I want to define the pocket diameter. I'm going to keep it next to this initial ball diameter. And I will say pocket underscore diameter, just the 3 letters to keep it short, is equal to 66 pixels. I also want to keep track of the balls that have been potted. So I will set up another list here at the bottom, which will be potted balls. And this will be an empty list. Now we need to define the X and Y coordinates of the center points of each of these pockets. Now I've already gone through this image and worked those out, so I'm going to paste them over to save typing it all out again. So we'll scroll down, now we've got this section here for creating the balls, then we set them up, and then we create our cushions. So maybe just before we create the cushions, we'll add a comment here to say create 6 pockets on table. And this is where I'm going to paste the coordinates. So you can just copy this from the source code. It's essentially a list that contains 6 values, which are all tuples, which have the X and Y coordinates of each individual pocket. Now all we need to do is look at each ball, look at where its coordinates are, and see if it's gone into one of these pockets. We'll go back down into the main game loop, and just near the beginning, so before we even draw the pool balls, we will first of all check if any of them have been potted. So we'll add a comment here to say check if any balls have been potted. And to do this, we want to iterate through each one of them. We'll say for ball in balls, which is the full list of PyMunked objects. And then for each one of those in turn, we want to compare them to each of the pockets. That means we need another for loop nested inside here, which will be for pocket in pockets. Here we'll apply a little bit more trigonometry. So first we need to work out the horizontal distance between each ball in each pocket. So we can say ball underscore x underscore dist is equal to the absolute value. So it doesn't matter if it comes out negative, we will always get a positive value from this. Ball.body.position at index 0, which is the x coordinate of the particular ball, minus pocket at index 0, which is the x coordinate of that particular pocket. So as we work through these two for loops, we will be checking each ball against each pocket. So we'll look at the x coordinate first, or rather the x distance. We can then copy this down and repeat for the y distance. So ball y distance is the absolute value of ball body position at index 1 minus pocket position at index 1. Now we'll use a bit of Pythagoras to take these two and combine them into one distance value. We'll say ball underscore distance is equal to the square root, so math.sqrt, short for square root, and then within the brackets we want to square each of these distances. So this first bracket is going to be ball underscore x underscore distance, and to square we just add the multiplication symbol twice. So that's the first one squared, then we add the same thing for the y distance, and we square that one, and then we just add another bracket at the end to close them out. This gives us the distance between the center of the ball and the center of the pocket. So to be able to determine whether the ball has fallen into the pocket, we just need to check if that distance is less than the radius of the pocket. And we can add that check here by saying if ball underscore dist is less than or equal to, well, we've already defined the diameter of the pocket, pocket underscore dia, and we just divide that by 2 to give us the radius. If that ball has been potted, there's a few things we have to do here. First of all, we need to remove it from the PyMunk simulation. That means we need to remove it from our space. Say space.remove ball.body. We also need to remove it from the overall list. So we can say balls.remove ball. Now that they're removed, we want to be able to track which ball has been potted. Now remember, we created an empty list called potted balls. So now we need to add the image of the ball that's been potted into that list. But how do we know which image that was? Because remember, this balls list just contains the PyMunk objects. The actual images are stored in another list, which is ball underscore images. Well, what we need to do is figure out which one of these balls it was that's been potted. And we can do that by enumerating this for loop as we've done previously. So by simply adding an additional variable I at the beginning, and then wrapping this in enumerate, we'll be able to keep track of the index that we're working through this list at. So as we work through the list and we pick the next ball and the next ball and the next ball, this I variable goes up with it. So we can then use this I variable to pick the corresponding image. We can go into our potted list now, so the potted underscore balls dot append, and what we're appending is taking an image from the ball underscore images list at index I, which is this variable here. And lastly, because that image is now being removed, or rather that image is now being moved into another list, we need to make sure that we delete it from this original list. Otherwise we're going to have too many images in this list that won't correspond with the number of items in this list. So to do that, we say ball underscore images dot pop at index I. So that was quite a lot. Let's just test out and see if this works. I'll add a temporary print statement down here in the main game loop, which will print potted balls. Let's run this again. And to start with, you can see it's just an empty list. Now it may take me a little while to pot something here, so you might have to bear with me. I had to fast forward this because it took me a little bit too long to actually pot something, but eventually I got one. Okay, and now you can see I potted that ball, and we've now recorded that there is a surface here. So an image has been added to this potted balls list, and we lost the ball from the screen. So that's good. We know that the code is working, but visually that's not a very good indication of keeping track of these potted balls. What would be handy is to have some kind of little panel, maybe down here at the bottom of the game window, that just displays all the balls that have been potted throughout the game. So to do that, we go all the way back to the top where we define the parameters for the game window, this width and height, and we could just increase this height here, make the window bigger, but instead I want to keep this as it is, and I want to add a separate variable which will be called bottom underscore panel, and I will set this to 50 pixels tall. I can now carry this over into this section here, so when I create my game window, I define my screen width and my screen height. Well, for the screen height, I will add the bottom panel. If we run this again, now you can see there's a tiny little bit appearing down here. So we've got an extra panel down below the actual pool table that we can use to fill in with additional information. So let's go down into the main game loop and change how we display these potted balls. We can remove this print statement. We don't need that anymore. That was just temporary. And then we will come back to this section here because there's a little bit more to add to it. But for now, we go down to where we've got our pool cue being drawn and then powered up. And just up here, so just above the event handler, we will add another little section with a comment to say, draw potted balls in bottom panel. Well, since we already have a list, we can just iterate over it. Now I know that I'm going to need to keep a tracker of it, so I'm going to enumerate from the beginning. I will say for I, then comma ball, and enumerate potted balls. So we go through that list, we look at each individual ball that's been potted, and then we track the index of that. And now we can call screen.blit to allow us to draw these balls onto the screen. What it is we want to draw is that particular potted ball in the order they've been potted, which means that in the order they've been added to this list. Then we define the X and the Y coordinates. So for the X coordinate, we just want to offset from the left a little bit, so it's not bumped up right against the edge of the screen. So we'll put 10 pixels plus, and now this is where this I variable comes in, because if we have just one potted ball, that's okay, we can put it at pixel 10, but if we have 4 potted balls, we want to make sure that each one of them is staggered from the one to the left. So we use this I variable here and we multiply it by 50. So they will be spaced apart by 50 pixels. So that takes care of the X coordinate. And for the Y coordinate, well, the reason I didn't add anything to my screen height variable and created another one for my bottom panel means that I can still use my screen height as the overall height of the game area, which is just where the pool table is. So we add onto this 10 pixels. So now let's run this again and see if we can get it working. I'll try and pop a couple of balls just so we can see them stacking up next to each other. So that's one, and there's the second one. Okay, that took a while, but you can see I potted them in the same order that they're being displayed down here. So that's working pretty well. You'll notice one thing though, is that the pool cue just kind of slides over into that area. We don't actually want to be able to see the pool cue down there because that's not part of the game area. That's just our little panel for displaying information. So we want to cut the pool cue off about this line here. So to do that, just before this section where we're drawing the potted balls, we will add another little section. We'll add a comment to say draw bottom panel. And all we'll do here is just draw a rectangle over that panel. We'll call pygame.draw.rect. We'll call it onto the screen. We need to define the color. Well, it needs to be the same color as the background, so BG. And then we define the X and Y coordinates and the width and height. The X coordinate will be 0, Y coordinate will be the screen height, so that it starts right at the bottom of that game area. And then the width will be my screen width, and the height will be the height of the bottom panel. So let's try this again. And now as I rotate around, you can see the cue ball, or sorry, the cue disappears when it goes to the edge of that screen, and we can't see on the bottom panel. Now I mentioned earlier that we're going to come back to this code up here where we check for the balls being potted. And the reason for that, I'll demonstrate. So you saw me potting some of the balls, albeit with great difficulty, and that seems to be working fine. But what if I pot the white ball? Well, now the white ball has gone in here, and essentially what the next ball along was becomes the new cue ball. So now this number 15 becomes my new cue ball. And that's simply because the way that this code works is that it just looks at the last ball and takes that as the cue. So if I potted that 15, now the 14 becomes the cue. Of course, this isn't what we want to do. So what we want is to have this cue ball treated a little bit differently to the way the other balls are handled. So in this section here, where we check if a ball has been potted, we want to add a little comment to say, check if the potted ball was the cue ball. So how do we actually check this? Well, we know that the cue ball is always the last item within this ball's list, but the ball's list is always going to shrink. Every time we pot a ball, we remove the ball from it. So this ball's list shrinks over time. That means that we need to check how long that list is. We need to see how many items remain inside it. Then as we iterate through this for loop, we keep track of the index that we're at. So when we get to the very last ball within this list, this I value will be greatest. So essentially, we just check whether this I value is equal to the length of these balls minus 1. And that's going to tell us if we're at the end of the list. So we add an if statement here, if I is equal to the length of the balls list minus 1. The reason we have to subtract 1 is because length is going to give us the total number of objects in there, but I is the index value which begins at 0. So if there are 5 balls, this will return 5, but the index will be 4 because it starts counting at 0. So we just subtract 1 to bring them to a level ground. So if that's happened, then that means that we've potted the white ball. So we'll pass for now, because we'll deal with that in a second. But if that's not happened, then that means we've potted one of the other balls. So we put else, and then we indent all of this stuff underneath within this else statement, because that still happens. So if we potted any of the other balls, we apply it just as we did previously. So if the cue ball is potted, what do we do with it? Well, normally we would just reposition it back at the starting place. However, if we do that, as soon as we potted the white ball, if the other balls are still moving around, then they could end up colliding with that white ball. We shouldn't reposition it until all of the balls have stopped moving. So what we're going to actually do is just take the ball completely off the screen and off the game area. We'll say ball.body.position is equal to, and we'll just pick a number like minus 100, minus 100. So that takes it completely outside of our game area. And we also want to make sure that it stops moving. So we say ball.body.velocity is 0.0 in the x direction and 0.0 in the y direction. So let's test this and see what happens. Now if I pot the cue ball, well, nothing looks like it happens, but we're not showing it down here anymore. So we know that it's being treated slightly differently from the rest. The cue ball is now somewhere away over here at minus 100, minus 100. So what we would normally want to do is reposition the cue ball back here. However, if we do that immediately as soon as it goes into the pocket, if any of these balls are still moving, we could then have a potential impact with that cue ball, which will put it off. In reality, when you've potted the white, you would wait until everything stopped moving and then reposition it. what we need to do is add a little trigger here. So we'll add a trigger to say Q underscore ball underscore potted is equal to true. Now we haven't actually defined this as a variable yet, so we go to the top of the code where we're defining our game variables, and I'll keep it together with these other booleans. So I'll say cue ball potted is, well, it begins as false. We only want to reposition the cue ball once all of the balls have stopped moving. We already have a check for that. So if we go into our while loop, there's a section somewhere down here that says check if all the balls have stopped moving. And that is then determining this trigger variable here, this taking shot, which then in turn gets checked further down because we only draw the pull cue when everything is stopped moving. So we can just incorporate additional code into here that allows us to reposition the cue ball. So after this if statement, let's add another if statement that says if cue ball potted is true. So if we've potted the ball, but all the balls have now stopped moving, let's add a note to say reposition cue ball. To reposition it, we just access the last index value of the overall list, and then we say .body .position, and we just put it back to the start, or the start position, which was 888 on the x coordinate, and then screen height over 2 on the y coordinate. We also want to reset that trigger again, so cue ball potted now becomes false. So essentially, we've replaced the ball and we can restart the game. Let's just test this out, and I'll put the white ball here. Well, nothing was moving to begin with, so this just gets put straight back to how it was. If I was to hit one of these balls and then put the white, you would see that we would wait until everything stopped moving before that happens. But the chances of me managing that are pretty slim, so I'm not going to try and test that right now. So most of the game functionality is now there. The only thing I would like to add is that when we pot the white ball, there is some kind of negative effect from that. And what we'll do for that is just add a number of lives for the player. So we go all the way back up to the top where we define our variables, and we add another one which will be lives. So the player will start off with 3 lives to begin with. Now I want to display the number of lives on the screen in that little panel that we've got at the bottom of the pool table. So I need to do a couple of things. First, I need to create a new color for it. I'm going to display it in white, which means it's 255, 255, 255. I then need to define a font that I'm going to use. So I'll add a comment here to say fonts, and I'll define a couple. So font 1 is going to be pygame.font.sys font, and I'm going to use, I don't know how to pronounce this, whether it's Lato or Lato, maybe you can correct me. And then the size is going to be 30 pixels. And I'll paste this and I'll have another font which will be large font. The same code, but all I change here is just the size of it to 60 pixels. Now I've got my color defined, I've got my fonts defined. Now I need to define a function to allow me to actually print text on the screen. Pygame doesn't have that by default, so we have to create our own helper function. Add a comment to say function for outputting text onto the screen. Define draw underscore text. So the arguments this will take are the text, the font to use, the text color, and then the x and y coordinates where we display this text. And all we do is, first of all, we take that text and we convert it to an image. So img is font.render, render the text, and we pass the text color. Once that's done, we blit this image onto the screen. So we call screen.blit, use this image variable which we just created, and blit it at coordinates x and y, which we're passing through as arguments. That's our function created. Now we can go into the main game loop where we are drawing our panel, which is just down here. And before we draw, no, rather it'll be after we draw the rectangle. So we draw a rectangle first, that overrides anything that's down there, and then we draw our text on top of it. The text will say lives, with a colon and a little space, plus string of the lives variable. So we can't just add the integer value because it's a string here, we convert it to a string first. The other arguments were the font that we want to use, so it's just a regular font, the color is white, and then the coordinates will be screen width minus 200 because I kind of want it coming in on the right hand side, and screen height plus 10. Okay, let's try that. And there we go. We can see down here is displaying our lives. Lives 3 is what we started with. If I put the white, nothing happens. It still stays as 3. So we actually need to subtract 1 from the variable whenever we put the white ball. Now we go back up to where we were checking for potted balls, which is in here. And then this is the section where we check if the potted ball was the cue ball. So within this if statement, the first thing we'll do is just subtract 1 from lives. Lives is subtracted by 1. Let's try this again. And now as I pot the white, it goes to 2, 1, 0, -1, -2. Okay, so we're most of the way there, but of course we need to deal with the fact that we can just keep playing and go into negative territory with lives. So let's go back down to where we're currently drawing our panel, which is this section here, drawing the bottom panel. And then underneath that, we're drawing the potted balls inside it. So just below that, above our event handler, add another comment that says check for game over. And this will be if lives are less than or equal to 0. So if we run out of lives, well, let's just display the text to tell us this. Draw underscore text. The text is going to be all caps game over. This time we're going to use that large font that we created. The rest will be very similar. It's going to be white, screen width over 2 minus 160 pixels for offset. And then height wise, it'll be screen height divided by 2 minus 100 pixels for the offset. So let's try this again. And if I just keep putting them in, 2, 1, okay, we've got this game over coming up, but I can still play the game. I can continue trying to pot balls, and in fact, I can just continue potting the cue ball. So we need a trigger here. It's not enough to just display the text. We need a trigger that will record the fact that we've gone to 0 lives. And that trigger is going to be a variable that we haven't defined yet, but we will in a second. So when this condition is met, we will draw this text and we will also set game underscore running. Oops, spelled that wrong. Game underscore running is now set to false. So this will be our new trigger for checking the game state essentially. But of course we need to define that variable before we can use it. So let's go all the way to the top where we're defining our variables, and we'll keep it with the other booleans. We'll say game running is true. So it begins as true. So that means that as long as the game running variable is set to true, we just play as normal. But as soon as it's set to false, we don't want to be able to display the cue, we don't want to be able to aim, and we don't want to be able to take any more shots. So we just need to add this condition as a check to a couple of if statements that already exist. We go down into the game loop where we look for the section where we're drawing our pool cue, which is just here. And it currently says if taking shot is true, then we carry on. Well, we can add this check into here as another statement. So we'll say and game running is also equal to true. So that will stop us from drawing the pool cue and moving it around. However, we will still be able to power up the pool cue because that's a separate check. So we need to add that condition here as well. So we say and game running is true in here. So let's just test this out. And I'll just start potting the white ball. So once we get down to 0, the cue disappears, the ball is repositioned, but if I click anywhere, it doesn't matter. I'm not able to power up anymore, and I'm not able to take any more shots. There's only one more thing that we still need to add. At the moment, we have a game over check, which is when we lose all our lives. But what about when we pot all of the balls? Well, we need an equivalent. So we'll just copy this down and put it just below. It's going to be a very similar check, but we change the comment to say check if all balls are potted. The way we'll know that is by looking at the length of that list. We'll say if len balls, which is the one that contains all of the PyMunk objects for the balls. Now you could say if that's equal to 0 means that everything's been potted, but remember we still want the cue ball to not be potted. So this will have one ball left in it at the end. So once everything else is potted, we'll still have the cue ball available. Then we draw text instead of game over. It says you win. We'll use large font, white, and the coordinates. I think we can keep them exactly the same actually. The text is more or less the same size. And then we still have this variable game running is false so that we can't just keep shooting the cue ball around. Now if I try to put all of the balls to demonstrate this, it would take a very long time. So what I'm going to do instead is go to the top where we're creating these balls, which is this section here. And instead of 5 rows by 5 columns, I'm just going to set both of these to 1. So what I should end up with is one ball here and then one ball here. Now this is my cue ball, but because I haven't loaded all of the rest of the images, it's just taken the next one in the sequence. So it's taken number 2, but we'll just treat this as the cue ball for the purpose of this example. So now I will try and pot this ball, which may take me a while. And there we go. It comes up in the exact same way. I can no longer move the ball around. We've detected that we've potted the ball, and it says you win at the top. So I'm going to revert this back to 5, just make sure that it's all set up correctly. Yep, okay, and everything's working as it should. So I hope you guys found this useful, and if you did, please leave a like and subscribe to the channel. And if you have any ideas on other tutorials that you would like to see, then just put them down in the comments below. Thanks for watching.